My name is William Horn, and I decided to do my data mining project on some data from the Alaska Satellite Facility. So some background on the data set. The Alaska Satellite Facility's goal is just to make satellite data more accessible overall, and Vertex is one of their tools for making that happen. It's a data portal for searching and downloading remotely sensed imagery from the Earth. And then from that site you can download a CSV metadata file that describes all the different data that you can download. So this metadata is what I decided to data mine. It's a file that you download from Vertex. After you're done searching, you select a bunch and then you can download the file that describes all the records that you selected. Each instance has a bunch of lat-long numeric data, dates when the data was acquired, some attributes that describe the sensor and what satellite was used, and then there's some product info, which is mainly just the size of the data in total. So the goal is to make a prediction on the platform attribute. This is a nominal attribute. It can be either Sentinel-1A or Sentinel-1B, and this indicates which satellite that the data was gathered from. So you can see from the picture all the different attributes that are in a single instance, and this is after a lot were cleaned out. So also you can see that the percentage of my sample isn't exactly 50-50, and that'll come up later in some of the different algorithms. And this is totally made up because every metadata instance has the platform attribute. It was just something that was easy to make a prediction on, so that's why I picked it. So to clean the data, I wrote a little Python script. The size in megabytes column, instead of just having a number, it had a number and then followed by megabytes. So when I was trying to convert it to R format, it was counting it as a nominal attribute and not as a numeric one. So I just went through in the script and removed that megabytes so it would work as a numeric attribute. And then also removed a lot of columns, a lot of empty columns, ID columns that just had some text in them that wasn't really relevant, that was just consistent through each instance. And then also a lot of the dates, when it got converted to R format, it was just treating them as nominal attributes, so that wouldn't have been helpful. It would have acted just like an ID. And then also some of the attributes mapped perfectly to the platform, so I took those out because it wouldn't have been any. I wanted to see what would happen, how the algorithms would handle it. Because initially when I first ran through, 1R gave 100% classification, so I wanted to be able to really compare the different algorithms and their performance. This is just a side note on Python. I really like some of the syntax that it allows, and so one of those that I used when writing the cleaning script was list comprehensions, which is what you can see in the picture on the right. And that's just removing all of the deleted rows, and the cleaned row is just, you can see this, there's a set operation where it subtracts the deleted indexes from all of the indexes in that row, and then adds the row index I is just adding that to the list, the overall list. So it only keeps the rows in the CSV that don't get deleted. Yeah. So this is the overview of the ARF data set in the Weka Explorer. Right now beam mode is selected, so you can see the different distributions of Sentinel-1A and 1B and what their beam modes are. I looked through most of the attributes, and there isn't a really clear separation after all of the directly mapped attributes got taken out. Especially a lot of the lat long data seems to be pretty randomly distributed, so it'll be interesting to see what the different algorithms do with that and how they deal with that. The first algorithm that I ran on the dataset was 1R. With the original data, it gave 100% correct classification, and so that's why I decided to remove some of those attributes, because that wasn't interesting. Also, it picked the far start long attribute to predict on, which is a numeric attribute, so I thought that was also kind of interesting that it ended up picking that one. 70%, that's not really that great, but as a first pass through, it's not bad. So this is the cost benefit curve for that 1R run, and what I kind of got out of this was that you can see it minimizes at 40% of the sample size. So that kind of came up later in comparing one of the better algorithms, which minimized at a higher sample percentage of the sample size. The next algorithm that I ran was a clustering algorithm called EM. I'm not sure what that stands for, but it was not very good on this data set. With running just the default Weka settings, it gave around 50% incorrect classifications, which is not just like flipping a coin. Some of the performance boosts came from directly setting the number of clusters to 2, and then what gave most of the increase in performance was ignoring all of the lat long values except for center lat and center long, and taking a look at the classifier visualizer kind of maybe shows a little bit why that is. So you can see this is a cluster visualizer, and there's not really a definitive separation of the instances in any of the attributes, but you can see those kind of 8 different repeated patterns. Those are all the lat long values, and so maybe having multiple repeated of those gives maybe a misrepresentation and maybe tricks the clustering algorithm a little bit. It doesn't add any new information from the extra lat long, but it is helpful to have a pair, so I thought that was kind of interesting. So next came the association rule mining. This was not very good, not a very good algorithm for running on this data set, mainly because most of the attributes are numeric, and numeric values are not allowed with these algorithms. So what I assume the minimum support was how many instances actually were covered by the rule. And so also one of the performance boosts came from setting the number of rules down from 10 to 2, and I assume that's just because with such few number of actual attributes that it had to work with, having a large number of rules didn't really add anything, just maybe forced it to make some bad rules. So yeah. Next is the just free-for-all algorithms, which is mostly classification, because those seem to do the best. Yeah. So the first algorithm that I decided to run on was the logistical model trees, and this algorithm did pretty good. 91.8861% correctly classified instances, which translates to only 151 misclassifications if you look at the confusion matrix, or just says it right in the printout. But if you take that positive sloping diagonal, you can get the total misclassified instances. One little performance boost came from increasing the number of folds on the cross-validation from 5 to 10, but I'm not really sure why that would happen, because I thought that was just the testing that was happening and not the actual creation of the model. But it gave a higher percentage, so yeah. This is the output tree from running that algorithm. It looks like that this algorithm could really take advantage of that numeric data by creating this pretty complex tree, because there was lots of different attributes to branch on, and hopefully the data is not too the model's not too overfitted. But yeah, makes a pretty complex looking tree. And I also thought another thing was interesting was that the same attribute appears multiple times at different levels in the tree, which I mean, if it helps, it works, but I didn't think that was a thing that would happen. Next algorithm I ran was K-star. This is another classification algorithm. It has pretty good performance. 93.17 correct classifications. One thing to note is that it ran really quickly, almost instantly, which is really impressive for how well it classified. Another thing to note is that an emerging trend in all of these algorithm runs is that it gets overtrained on Sentinel 1A. So if you can see in the confusion matrix, it picks 1A more even when the actual instance is Sentinel 1B. This holds from what we learned in class, where if you want to weight something, you just put more instances of that into the training set. So you can see the percentage of 1A to 1B. You have 59% 1A versus 41% 1B, and this leads to 1B being more misclassified more and 1A being misclassified less. Next algorithm I ran was multi-layer perceptron, which sounds like a neural network to me, and unfortunately it's not very good. It was really slow to run, and it only got 80% correct classification. There was a performance boost from increasing the number of training epochs, but this really slowed down the algorithm, and I could see that maybe if you had 10,000 instances, this would become really a problem. So it does bring up the point of computational cost versus performance, and if not just in a dummy sense, because it really only took 9 seconds overall, but it raises the question. Next algorithm I ran was the randomizable filtered classifier. Did pretty good, 92.2%, and it was really affected by the disproportionate data, because on the last K-star, I think, was 67 misclassified 1B instances, and this one had 83. So yeah, whatever it did behind the scenes, it was really affected by that difference. So the last algorithm I ran was the random forest, and 96.83% correctly classified instances. That is the best so far, and I think that this algorithm did the best overall. Yeah. Looking at the cost-benefit analysis for this curve, you can see that the curve minimizes at 60% of the sample, which is, if you compare that to the 1R, or even, I didn't show it, but another algorithm that I ran actually had the same 0.4% minimization sample size. So this one having 60%, minimizing at 60%, might explain why this algorithm did so much better than the other ones. So I decided to choose the winner based on just which one had the highest correct classification percentage. There's not really a difference in misclassification versus 1A and 1B, so that doesn't really need to be taken into account. So if we just look at all the percentages, it looks like there's a lot, half of them are kind of hovering around that 90 percentage, and then the other half are below that, and random forest seems to take it pretty decisively. But just to be sure, I did the calculations for the paired t-test, the paired data t-test, and if the one thing that I wasn't sure about was the estimation on the standard deviation for the sample, but just copying what was on the example project gave me a pretty high t-stat of 38.2. So also I did a right-tailed test, so just checking to see if the random forest, the difference in the random forest versus the k-star is greater than 0. So if k-star has a higher percentage than, or if for the random forest has a higher percentage than the k-star, then that difference will be positive. So just checking that with the test hypothesis. K-star, so and that's with a confidence level of 99%. But you could increase the confidence level probably even more, and this right term wouldn't overpower 38.23. But yeah, I'm not sure if this number is correct. Yeah, just because the standard deviation might have been calculated wrong, but hopefully not. So that's it. Thank you.